No. Don't be shy. You're watching Beau Math. Nothing to be afraid of. Come over. Got something for you. Pick a card. No, not that one. Pick a card. No. Is this your card?
Hello everybody and welcome back to another episode of Beau Math. In the last video, we talked about yet another perspective we could talk on fractions, and that was looking at chance of things, how likely or unlikely an event is. And this was the idea of probability. And we talked about a few different ideas with probability. We talked about the complements of things, which is basically the opposite event happening. We talked about how to actually calculate probability, how to apply probability to different situations, how to do a sort of experimental sort of probability, which was called the relative frequency. And lastly, we looked at kind of a more theoretical idea of how we can relate the relative frequency to the probability by using something called the law of large numbers. As always, we're going to do some gnarly practice here. I've got the problems up on the screen. So as always, try those out for yourself first. And once you've given a good honest shot at that, let's go through the answers together. Question 1. Suppose there is a 1 in 10 chance that my mother calls me on any given day. How many times would we expect her to call me over the course of a year? Alright, so the probability here is 1 in 10. Or if we want to put that as a percentage, that's the same as 10%. So it's not super likely, but there's still a chance that I get a phone call from my mother, a 10% chance specifically. So now what we want to do is we want to see, okay, if it's roughly 1 in every 10 days that I get a phone call, well, then over the course of a year, how many times would I expect to get a phone call? Because of course that's a lot more than 10 days, right? So all we have to do is we just have to apply this probability, this proportion of chance, right? And we know that applying proportions is done through multiplication. So we do 1 in 10 and we multiply it by 365 because that's how many days there are in a year. We're assuming it's not a leap year, even though this year it was. And multiplying these, we get 365 over 10, which slides the decimal over by 1, and we get 36.5. So, of course, she can't phone me half of the time, so we're going to have to choose to round this, either up or down. It's usually standard to round up, so let's be generous, and we will round up to 37 phone calls would be what I get over the course of a year from my mother. And by the way, this little symbol I use here just means it's approximately equal to, because obviously 36.5 isn't exactly 37, but we're rounding it up to 37. So you may see me use this symbol every now and again. But yeah, that was question 1, just applying a probability, just how we applied proportions to groups of different sizes. Question 2. Alright, so question 2 says, for each event, describe what the complement would be. Remember, that's the opposite event. And what the event the complement actually represents. So for part A, the event we're talking about is there's a 20% chance my McDonald's meal will be cold. So the event is our McDonald's meal cold or not? And the chance of it actually being cold is 20%. All right, so what is the complement of 20%? Well, what makes 20% into 100%? That would be 80%, right? 20% plus 80% is 100. So that means 80 is the complement of 20%. But what does that mean in this circumstance? Well, if 20% was the chance that our meal was cold, 80% would be then the chance that our meal is not cold, right? So 80% chance our meal is not cold. So it's more likely to get a warm meal than a cold meal from McDonald's, which is how it should be. Alright, for part B, this says, there's a 100% chance that you will get popcorn stuck in your teeth. I don't know about you, but this happens to me every time I have those little suckers. So, if we do 100%, what's the complement of that? So 100% plus what gives me 100? Well, we're already at 100, right? So the complement of this is going to be 0%. So 0% is the complement of 100. And that makes sense because 100% is guaranteed. 0% is impossible. What's the absolute opposite of it's guaranteed to happen? Well, it's basically guaranteed to not happen, right? So that's impossible. The complement here is that there's a 0% chance that you won't get popcorn stuck in your teeth, right? That's the opposite event here. Right, and then for part C, you were just born. Congratulations. There's a 172 in 1,000 chance that you ended up in India. So what is the complement to that event? So the probability, this time it's not a percentage, this time it is a fraction. If we wanted, we could make it a percent, but it's also good to be comfortable with just using fractions. So we want to see what completes 172 over 1,000 to 100%. That's the same thing as what completes it to 1, right? Because 1 is the same as 100%. So what completes 172 over 1,000? Well, we know that 1 is the same thing as 1,000 over 1,000. So we essentially want to see what makes 172 into 1,000. We can just do that by doing 1,000 minus 172, and we get 828. So that means 828 over 1,000 will be the complement of 172 over 1,000. Because if we add these up, we will get back to this 1,000 over 1,000 or 1. So that means there's an 828 in 1,000 chance you won't be born in India. All right, so those are some practice with using complements. If you want some more practice, just make up an event that has a certain probability. You can completely pull the number out of nowhere. Just make sure that the number is either between 0 and 1 or 0 and 100% because you can't have probabilities that are outside of that range. And then calculate the complement of that event, and also make sure to understand what the complement actually represents. We can all say that the complement of 20% is 80%, but it was important to add this context of it being the opposite kind of event there. All right, so that's question 2. Let's move on to the third one.
Question 3.
All right, so we got a true or false question here. The law of large numbers guarantees that the relative frequency for 100 trials will be closer to the probability than the relative frequency for 10 trials. The law of large numbers basically said that the more trials you do, the closer your relative frequency will get to the probability. Now, that was not 100% true, and here I'm going to kind of clarify a little bit on that, because this right here is actually going to be a false statement. Even though it's more trials, we could technically get a situation where I do 100 trials, and one of those trials out of the 100 occurs. So this ends up being our relative frequency, right? So let's say we're flipping 100 coins. So I do 100 trials. I want to see how many give me heads, but only one gave me heads. So the relative frequency was 1 out of 100. But I could also have a situation where I do 10 trials, and I get 4 out of those 10 are heads. Now, we know that the probability of getting a heads is 1 out of 2, right? So if the probability of getting heads is 1 out of 2, we actually see that the 10 trials had a closer relative frequency to the probability than the 100 trials did. And this is possible, right? Even though it's extremely unlucky that we get 1 in 100 trials being heads, it still could happen, right? This seems like something that would contradict the law of large numbers, which would claim that, well, these 100 trials, since it's more trials, should have a probability closer to a half. So this is where it gets a little bit complicated. Technically, no matter how big of a number we have, we could always get super unlucky and have a relative frequency that's less accurate to the probability than something with way less trials, right? I could even do something like 1,000,000 trials and get a relative frequency that's even worse, right? 1 in 1,000,000. This is super, super unlikely, but I technically could get this, right? So even though we have a super big number here for the amount of trials, we could get a relative frequency that's way off from the probability, even more off than what we measured for a super small amount like 10 trials. And so is the law of large numbers just completely bogus? Well, no. What's kind of happening is, notice what I said here. We got extremely unlucky to get 1 out of 1,000,000, right? It's technically possible, right? 1 in 1,000,000 things do happen, but it's super unlikely, right? And so the point is that the bigger the number gets, right? So 1,000,000, 1,000,000,000,000, 1,000,000,000,000, right? The bigger the number gets, that kind of getting super unlucky becomes too unlucky, right? There's such a thing as something that was too lucky or something that was too unlucky. So the bigger the number gets, it becomes less and less feasible for something like this to happen, right? If this is unlucky, this is mega unlucky, eventually it gets to a point where it's so unlucky, it just can't happen. It's just not possible. And so that's kind of what the law of large numbers is actually saying. It doesn't guarantee that your relative frequency is better. It doesn't guarantee your relative frequency is going to be closer to the probability, but you have to get unluckier and unluckier and unluckier to have that relative frequency be off from the probability, right? And so eventually, as you go to infinity, it becomes so improbable that your relative frequency is that bad that essentially it has no choice but to kind of go towards the probability. So I hope that maybe clarifies what I didn't talk about in a ton of detail in the last video, just because I was trying to get the idea across. But yeah, so this is a false statement. It doesn't guarantee the relative frequency is better, but eventually when the numbers get large enough, it essentially does because the probability is so low. So this is false.
Question 4.
All right, so this one is just simply we have several events and we want to calculate the probability of them happening. So remember, to calculate the probability, it's the amount of possible times what we're looking for shows up divided by or out of the amount of possible events. So for example, what's the probability of rolling an even number with a d6 or a six-sided dice? So on a six-sided dice, there are 6 possible outcomes, right? Numbers 1 through 6. And an even number, well, how many even numbers are there? Well, half of the 6 numbers are going to be even, right? 2, 4, and 6. So that's 3 out of the 6 numbers that are even. So 3 out of 6 simplifies to a half, or 50%. So there's a 50% chance of getting an even number when you roll a d6. All right. What if you rolled a d60? So that's just a 60-sided dice. It's the same kind of thing, right? If you have 60 numbers, half of them, or 30 of them, are going to be even out of the 60, and we will also get a half. So it seems like it doesn't really matter the amount of numbers on our dice. We're going to get the same probability because even numbers always make up of half of the numbers regardless of how many sides are on your dice. The only exception to this would maybe be if you had something like a d5. So this is a 5-sided dice. So that has the numbers 1, 2, 3, 4, and 5. Well, there's only 2 out of the 5 numbers are actually even on that one. So if you have an odd number of sides on your dice, then it's not going to be 50%. Then it's, in this situation, going to be 40%. All right, so let's move on to part C. So what are the odds, what's the probability of rolling a 7 on a d6? Well, d6 has only 6 sides, right? 1 through 6. 7 isn't among those numbers, right? 7 comes after 6. So how many 7s are on a d6? None out of the possible total, which is 6. So what does that make our probability? It makes it 0, right? There's a 0% chance of it happening. This is impossible. You can't roll a 7 on a dice with 6 sides. And for the last one, this says rolling a multiple of 5 on a d20. Okay, so between 1 to 20, how many numbers are a multiple of 5? We can quickly list them. We got 5, 10, 15, and 20. So there are 4 numbers between 1 and 20 that are a multiple of 5 out of the total possibilities that the dice could roll, which is 20 different numbers. And that simplifies to 1/5 or 20%. So there's a 20% chance that you roll a multiple of 5 on a d20. So not great, but not the worst. And if you want some extra practice, choose some criteria for the numbers on a dice, and with however many sides you want. You know, it could be a d30, it could be a d41, and just find the probability of that event occurring, right? So you could say, what are the odds that I get an odd number on this dice, or what are the odds that I get maybe a number that is a multiple of 11 on this dice, or something like that, right? So you can have some fun with getting creative with it. All right, let's move on to the last question.
Question 5.
All right, so this says that there are 52 cards in a deck of cards, and what's the probability of drawing an ace? So there's 4 suits in a deck, right? There's hearts, spades, clubs, and diamonds, and each of those has kind of 1 copy of each of the numbers, and an ace is 1. So that means since there are 4 suits, each with their own ace, there are 4 aces in a deck. So that means the probability of drawing an ace from a deck of cards, well, we know that there are 4 aces out of the total of 52, and that simplifies to 1 in 13, which isn't going to be that nice of a decimal. going to get approximately 7.69%. All right, so it's a roughly 7.69% chance, or a 1 in 13 chance of you drawing an ace from the deck. Now, suppose I draw one card to see if it's an ace or not. What are my two possible relative frequencies? So I only did one trial here, right? I just drew one card, so this is one trial. So that means my relative frequency is going to be out of 1, right? Because the relative frequency is measuring out of the amount of trials you did. And the only possibilities is I either get an ace, which would be one of my observed events, right? My observed event is seeing if I get an ace. So that would be 1 out of 1, which is 1. Or I don't get an ace, but it's still out of that one trial, in which case it would be 0. So our possible relative frequencies are only 1 or 0. And those are quite different than the actual probability. And this kind of reemphasizes the utility of the law of large numbers, because we did such a small amount of trials. We did like the minimum amount of trials here. And both of our possibilities that we got from that, neither of them really reflected what the actual probability was. Neither of them even gave us like a close idea of what it was. So this kind of emphasizes that we need more trials in order for our relative frequency to actually start resembling, or even have a chance to start resembling, our probability.
Mathematicians and data nerds would want you to believe that you need to do millions or even billions of trials to get closer and closer to an absolute frequency of true probability. You know how much time and energy you would need to dedicate to do something of that scale? Ridiculous. And importantly, it's not needed. And I'm going to show you right now. In my hand is a simple 52 card deck. There are exactly 4 aces in this 52 card deck, which means I have a 1 in 13 chance of pulling those cards. Now, with absolute frequency, they'd want you to believe that this might not be true over time, but I'm going to show you that I have certainty on my side. You see, every single pull is a number of that 52. So whether or not it's exactly an ace doesn't matter, because every single trial is accounted for in the 52. And I know that eventually, after enough cards, I'm going to find my aces. 1, 2, 3, 4. 52 cards and exactly 4 aces. Relative frequency, true probability. I'm struggling to see a difference. Read it and weep, math.
This man is a charlatan.
So Aidan claims that if there's only 52 cards in a deck, then you only need to draw 52 times before your relative frequency is exactly your probability, since you're guaranteed to get your 4 aces out of the 52 cards. Why is this wrong? So we've got 52 cards in a deck, right? 1, 2, 3. I'm not going to draw them all out, right? But we have 52 cards here. And if you draw one of the cards, right? So we draw this one here. That's either an ace or it isn't an ace, right? So if it was an ace, we would add 1 to our observed event, right? The observed event being getting an ace, we would add 1 to that. And if it was an ace, we wouldn't add 1, right? And the idea is, as well, if we just go through all of the cards, we will be doing 52 trials, right? Each one of those cards is a trial. And then because we've gone through every one of the cards, we're guaranteed to have gotten to the 4 aces, right? So that's looking pretty nice. It's looking like, hey, 4 aces out of the 52 trials. That's what our probability was. So we're good. The problem is what we're calling a trial here. What we're calling a trial here is picking a card, which is true, that is a trial, but it's a different trial every time, because if I just draw a card from here and I remove that card from the deck, The next time I draw a card, I'm not picking a card from the 52 in a deck anymore. I'm picking it from 51 different cards. So this is a different situation now, right? The probability is drawing an ace from a pack of 52 cards. But as soon as I look at this over here, it's now a different probability because now I'm looking at basically the chance of getting an ace from a pack of 51 cards where I've already removed one of them, right? And so this drastically changes what our results are going to be. The error in this was calling a trial drawing a card and then not putting it back. So the proper way of actually doing this would have been taking your cards, drawing a card from the deck, marking down if it's an ace or not, putting it back, and then reshuffling the deck so that each time you draw an ace, it comes from a pack of 52 shuffled cards, and that's not being tampered with. It hasn't been influenced by the previous draw.
Concluding thoughts.
So I hope that made sense to you, and I hope you're feeling a little more comfortable with probability ideas now. It's a really interesting area of math with a lot of super complicated ideas in it that someday we'll get into once we've kind of gone through a lot more math that's required to do that. But until then, you have a good one, you stay groovy, and I'll see you in that next video.